reason we don't see any extra dimensions is that there aren't any most serious people in the subject. Just stop working on the ideas that these things are failures. It's all about four dimensions.
What if our quest for unification in physics has been fundamentally misguided? Since the 1980s, string theory promised a unified framework, but after 40 years, it's failed to deliver. Now, a growing number of physicists are calling for a radical rethinking of our foundations. Enter Peter Woit from Columbia University, who earned his master's from Harvard and his PhD in particle physics from Princeton, known for his incisive writings on Not Even Wrong, his textbook Quantum Theory, Groups and Representations, and a fresh approach to a theory of everything. Woit isn't just pointing out flaws in mainstream fundamental physics, he's proposing something disruptively new. In this episode, we'll dive into the Standard Model, explore the problems with supersymmetry, and uncover why Woit believes that the solution to unification lies in understanding imaginary time. At the core of his approach are spinors, which researchers like Roger Penrose and Michael Atiyah call the most mysterious objects in the world. Welcome, Professor Peter Woit. It's an honor to have you back on the podcast again. It's your second round, I believe.
Yes, that's right. Thanks. I'm glad to be back.
Today you have a talk prepared for this conference called Rethinking the Foundations of Physics, and What is Unification is the theme of this year. So take it away.
Okay. And we'll see. I mean, this is fairly sketchy. I'll have to make some excuses for to really go into a lot of the things I'd like to go into would take quite a while, but I thought this is what I could do that I think I could try to convey it in a relatively reasonable amount of time. So let's just start with that. So what I wanted to do is first go over, what it is, at least to me, what unification is, what are the things that we're trying to unify, and then explain kind of what the kind of current paradigm for what this kind of unification might look like that we've been kind of living with for the last basically 50 years. And then, so I want to explain what that is. And then I want to say just a little bit about what I've been trying to do and what's gotten me very excited in the last few years, which is what to me, I believe is kind of a quite new idea about, about how to do unification, or about how to do a substantial part of unification in a new way, which doesn't have the same kind of problems as the things that we've been living with for the last 50 years. So that's just the outline. Okay, so to start, I mean, this is, you never know kind of how much to try to tell people about this. It's just kind of, there's a standard outline of what's the Standard Model. But, we have this incredibly successful theory called the Standard Model, and it's basically a fairly simple conceptually object, once you get used to certain kind of technical ideas about the mathematics and the physics, and it basically says that there are three forces in the world, and they're due to these U1, SU2, and SU3 gauge fields. There's the basically the electromagnetic, the weak, and the strong force, and then the matter is spin 1/2. Fermions, and there's some specific pattern of charges, which are the the couplings to these three different kinds of forces. And I won't write out. There's kind of a standard table of these. It's kind of an intriguing pattern we don't quite understand, but it's a pretty simple pattern. So that's forces, that's matter, and then the one probably most mysterious part of it is the Higgs field, and so this Higgs field is this space-time scalar field, which breaks the U1 and SU2 down to a U1 subgroup, and that gives masses to the weak to the SU2 gauge bosons and to the matter. So that's pretty much all there is. And so if somebody just tells you that, knowing the basics of the geometry and how this is supposed to work, you could reconstruct the whole theory. You can reconstruct the whole theory once I tell you the charges, and there's going to be a lot of undetermined parameters in the thing. Okay, so history. So this basically, we're kind of a bit over 50 years out from this.
Okay. So for here, just a quick clarification. See how it has U1 cross SU2, but then it goes down to just U1. And some people may be wondering, okay, you had electroweak unification, but you still have electromagnetism plus the weak force. Where did the weak force go? You're saying, correct me if I'm incorrect, that U1 is the only unbroken symmetry left after the Higgs mechanism. Okay, understood.
Okay. So the history, so this is pretty much, there's a long history of this, but it kind of came together pretty quickly in a few years. And, in April 1973, you could write down this theory and people started to realize that, what they had. And it took them a while to really, to gather the experimental evidence to be convinced that this was really the right thing. But it was there in April 73. Okay. And so now, the most amazing and bizarre aspect of this whole situation is that, this relatively simple theory, there are basically all experimental results, agree exactly with it. There's no such thing as some, interesting experimental result, which you can't, explain with this theory. And there's some technicalities about, the first version of this story didn't have masses for the neutrinos, but it turns out you can throw in some right-handed neutrino fields, and it all works exactly, as you expect so far. There isn't any data. The only kind of data that people talk about we're not sure what to do about often more kind of astrophysical data, things like dark matter and dark energy and questions about cosmology, but just questions that you can kind of study in an accelerator or by looking at matter at a short distance scale. Every experiment that we know how to do agrees exactly with this theory.
I see.
Okay. So this is kind of this is the problem of unification in some sense, that we're used to historically having experimental results which which disagree with our best theory and which tell you kind of what you should be doing instead, and we don't really have that. Okay, so now the other part of the story is general relativity, and so this is a theory which says that space-time is this 3 + 1 dimensional pseudo-Riemannian manifold. It's a kind of a standard kind of curved manifold, except one of the directions, the metric is kind of negative in one direction, and locally it looks like this Minkowski space-time. And then the gravitational force is described by the curvature of this space-time, and there's this Einstein-Hilbert action or the Einstein equations which tell you about this.
Mm-hmm.
But this is a classical theory. So we'll say more about this in later on. But the standard model is a quantum theory. This is a classical theory. But again, the history of this is basically in place 1915. So we've had it for over 100 years without changing, and it kind of has the same problem. It has that everything that we can do where we study the gravitational force, agrees precisely with general relativity. We just don't have kind of any kind of measurements or anything we see that disagrees with general relativity. Okay, so what's the problem? Well, both of these theories, that they're geometrical. There's a kind of a very basic symmetry story behind them, and once you understand the symmetry story, you can understand how to construct a theory, right, largely. But they leave the situation isn't quite satisfactory because there's some questions that these things don't answer. So there's no evidence that there's anything wrong about either of these, but there's some kind of unanswered questions. And maybe the basic one about the standard model is, why SU1, SU2, and SU3? It's what's the explanation for why those three gauge groups and why those three forces? And then part of the story is that for each of these things, you have kind of a free parameter, a coupling constant, which describes the strength of the force. And so there's three kind of numbers that come out of this, and one of them is the strength of the electromagnetic force, but why those numbers? And so it would be nice, we'd certainly like to have a better theory which would tell you something about, either tell you why the values of each of those three numbers, or tell you the ratios of them, or some extra piece of information about where they come from. Okay.
For people who don't understand this part, but they see these symbols, it seems like it's quite ad hoc. Like you have a circle here and you have a triangle and you have a square. It's like saying the universe is composed of that, and then you wonder, why is it a circle, triangle, and square?
Yeah, exactly. I mean, if you look at there's a long list of possible symmetry groups. So these groups, I mean, they're a little bit technical. U1 is basically just a circle. It's just a circle on the complex plane. You can think of it. SU2 is, you can think of it as, well, it's 2 by 2 unitary matrices with determinant 1, or it actually looks like a three-dimensional sphere.
Right.
SU3 is 3 by 3 unitary matrices of determinant 1. But why those three groups? I mean, they're among, if you look at the possible symmetry groups, Lie groups of this kind, these are kind of three of the simplest possibilities. But why those three? Why not something else? Why not?
Before we move on, the quick retort would be, well, no matter what it was, whether it was E8 or G2, we would still say, well, why E8? Why G2? No?
Sure. But I'll get to this in a minute about what yeah. So one kind of unification is to say, and maybe say something about this is that. So we'll see that anyway. Maybe give me a minute to get to that next.
Yeah. Okay.
To grand unification, and we'll say a bit about that.
Wonderful.
But this kind of is the problem. I mean, so one anyway. This is the general version of the problem, and then with the matter particles. I mean, so one question is kind of why are these things spin 1/2? Why are they fermions? Why are they spin 1/2? And then why do they have this specific pattern of charges? And this short list of kind of numbers which tell you how they're integers, which tell you how they couple to the U1, SU2, and SU3, and why that pattern of charges. And then they come in kind of three generations. They're kind of it's a pattern. You see the same pattern copied three times.
Mm-hmm.
Why all of this? So it's kind of small and manageable amount of kind of discrete structure, but where does it come from? It's not. It looks like there should be some explanation for it. The other thing is about the Higgs field. So the Higgs field is this scalar field, and you've chosen its potential energy so that it has a minimum away from zero, so it breaks the symmetry. And so where did this kind of potential energy function for the Higgs field come from, and why the Higgs field? The Higgs field is a kind of a complex doublet that transforms under SU2, and what's that about? And then why this potential energy function? And then the matter fields are all getting their masses from the strength of their coupling to the Higgs field. These are called Yukawa couplings. Why does each different matter field seem to couple to the Higgs field with some different parameter, and where do all those parameters come from, or what's going on with that? So those are some of the questions that you have just looking at this theory, that why it looks like there should be a better theory which explains these things. And then maybe a couple of other things to say about why we're not quite happy yet. So one question that's something that's actually not mentioned very often is that there's a technical problem. It still has never really been sorted out, is that when you write down this quantum field theory of the standard model, it's if you mostly do computations in perturbation theory using Feynman diagrams, and that's kind of an approximate calculation method. We know how to make that. That works fine. But we also know that that only works in the limit of kind of extremely small coupling. That for larger couplings you need a definition of the theory which which works for any coupling. And for SU3 and U1, well, for the SU3, we think we know how to do that. It's done using lattice gauge theory. You can write down this lattice discretization of the theory, and you can very explicitly say, here's how you would put it on a computer, and you do this computation, take a limit, you'll get that defines the theory. And if you start trying to put the matter particles in with that leads to some confusing and complicated things, but there are ways to make it work. But there still is no known way to really completely make this work for what are called chiral gauge theories in general, but specifically for this SU2. The SU2 couples differently to, we'll talk later about left-handed and right-handed spinors, but the SU, unlike the U1 and the SU3, the SU2 couples differently to left and right-handed spinors, and how to if you try and do that, if you try and discretize that and put it on a lattice, or if you try to find some other way of defining that non-perturbatively, it's still not known exactly how to do that. There's some pretty complicated proposals for what something it might work, but that's an open problem that's never really been resolved.
Okay,
and it's not often mentioned. Okay, and the more the problem that has gotten all the attention is that the general relativity is looks fine as a classical theory, but if you try to quantize it using kind of standard methods, you find this renormalizability problem. You find kind of infinities which you can't be handled in a standard way, and any way you try to handle them just is going to introduce an infinite number of new constants into the theory or something. So nobody really has there's maybe two ways to say this. Nobody has a really completely consistent, non-perturbative definition of quantum gravity, either by itself or coupled to the standard model, in the sense of, something that really you can show this is always going to give consistent answers and that you can calculate anything you want. But that's one way of saying it. But another way of saying it is that there are plenty of people who claim that, okay, they have an idea. Here's the idea. Here's a way to solve quantum gravity, whether it's string theory or loop quantum gravity or 100 other proposals. And many people claim to have kind of at least a plausibility argument that they've got a way to handle the problems of general relativity. So depending on how seriously you take these claims of people, you could say either there's no such thing, or there's actually a huge number of them. So we have, in some sense, if you believe everything that a lot of the string theorists would like to be true, they would like to say that string theory gives you such a thing, but it may give you kind of an exponentially large numbers of such a things, depending upon these questions about string vacua, et cetera. So, and anyway, there's maybe two ways to say the problem. One is that this problem, there is no solution at all. The other is to say that the world is full of claimed solutions, but none of them really seem to actually explain very much or have any way to test them or are satisfactory. So now I want to kind of start on what has been happening since April 1973, when it became clear that what these problems were was more or less immediately obvious. And so the first thing that happened is a few months later, Howard Georgi and Shelley Glashow came up with what's called the first example was called a grand unified theory. And so they were kind of addressing, I think, the kind of thing you were starting to ask about, which is, what happened? So they were trying to address this problem. What about these three groups with three constants? Maybe we can at least improve the situation by fitting them together as subgroups of one larger group, and either like something that was typically SU5 or SO10 they were talking about. And then, you only had this one group, and one thing that's very good about this is instead of having three coupling constants, you've got one coupling constant. So
right.
So this kind of if you do this, you end up with relations between the three coupling constants. And so then anyway, so you have to do that. You have to do that. The other thing you have to do is
just a moment. Sorry, can you explain that you get a relation between the three coupling constants from the one larger Lie group?
Well, there's only one. Yeah, I mean, anyway, if you write down the theory for one, or write down the theory for the bigger Lie group, it's just got one coupling constant in it. And then what you have to do is you have to explain why do we see why do we see the three coupling constants? But maybe I was going to come a little bit more to this in later. I mean, this is kind of the problem. The problem is that you have to, if there just was an SU5 theory, there just would be one number that determined everything. The problem is that we're seeing three things and three numbers. So you have to first explain why are we seeing three things, not just that one thing. And then once you have a model for why we're seeing the three things, that model has to explain, how you go from getting that one number to getting three numbers.
I see. Does it give you a relation between those three numbers?
Yeah.
Like some bound or some inequality?
No, I mean, so very precisely the way that this works is you set this up with a new kind of Higgs mechanism, and the new kind of Higgs mechanism is such that if you go above a certain energy scale, the so-called gut energy scale, which is like 10 to the 15th GeV, then all you're going to see the full SU5 theory, and it just looks like the SU5 theory. You're above. Anyway, yes, there's some kind of new symmetry breaking scale you had to introduce, and above that symmetry breaking scale, you do just have one theory. You have one coupling constant. So everything about the theory above 10 to the 15th GeV is written down in terms of these SU5 gauge bosons and one coupling constant. But then you believe you have to introduce the symmetry breaking at this so-called gut scale. And then once you introduce the symmetry breaking by a new set of Higgs or something, then you have to kind of evolve down to lower energies and say, what are we going to see at our energy scale? And you find that the U1 and the SU2 and the SU3 couplings, evolve differently as you change energy.
Mm-hmm. Okay.
But so you often see this graph of these three coupling constants,
right?
And then they kind of come together at a point, which is the point where they unify at this higher where they unify to SU5. Okay, but then the next thing you have to do is you have to say something about matter. So a technical way of saying it when I said you had a certain list of charges, that was another way of saying it technically is that you've written down a list of the irreducible representations of U1, SU2, SU3 that all your matter fields are fitting into and how they transform into those symmetries. And so you have to kind of do this. You have to explain how all those things, those numbers you get from the subgroups fit together into kind of one thing, how all those matter things fit together into a representation of the bigger group. So there, in some sense, you have a generalized notion of a charge for SU5, and you have to pick the SU5 charge of your basic particles and then look at and make sure that it gives you, when you look at the U1, SU2, and SU3 subgroups, that it gives you the correct list of charges that we know about. Anyway, so that's just a technical thing you have to do. But you can do both of these very nice, and it actually works out quite nicely for SO10. You can all the known particles fit together into one nice representation of SO10, the spinor representation. But then here's the problem is that you also have to introduce new Higgs. So you have to explain, why we don't see this big group of symmetries, why we see the smaller group of symmetries. So you have to, just as I was said that, we know that SU2 cross U1 breaks down at the energy, that the vacuum is only invariant under U1, we know that the vacuum it can't be invariant under SU5 or SO10, so you have to introduce some more dynamics that's going to break it down to this. And later you're going to break it down again to the U1.
Great summary.
Okay, so there's I know that Georgia and Glashow got very excited about this, a lot of people, because, this not only was, gave you a little bit of a pretty pattern of an explanation of some patterns in some of these numbers, but it also gave you some new predictions of some new physics, and in specifically, it's because you're putting this SU2 with the weak force and the SU3, the strong force, together. Quarks can decay into leptons, and so protons in particular are not going to be stable. That the quarks inside a proton or inside a neutron, let's say quarks inside a proton, are going to sooner or later at some point decay into another quark and a couple leptons. And you had a nice calculation of exactly how fast that should happen, and the initial numbers that they got were that this should happen, but very, very slowly. So it was perfectly consistent with the fact that we don't observe protons decay, and so people then started going out and doing experiments, looking for proton decay at the kind of rates that these things predicted. But then the problem was, and the basic problem since then has been that it turns out protons don't decay. I mean, people have kept building bigger and bigger detectors and looking more and more carefully for this, but there's just this just doesn't happen. Protons don't decay, and any of the kind of characteristic new physics you would expect from this, from having this larger group of symmetries, you just can't see any of it. You don't see any of it.
So it's not that we found proton decay is just smaller than the rate expected. It's that we haven't found any evidence for proton decay.
Yeah, and so, I mean, so these initial SU5, SO10 theories actually had kind of a very rough estimate of what proton. I mean, the problem is the exact rate depends like on how you do the Higgs breaking and various other things. But the so the initial kind of predicted rate, but by now I don't know I forget the numbers, but by now it's 10,000 or 100,000 times. And anyway, the bound is way above that. So
Got it.
So this is definitely wrong. And I know that so one thing that's true and interesting about Georgi and Glashow is that they actually did give up. I mean, part of the whole problem of the subject is people don't give up on these ideas. They did give up, and they stopped working on this. And if you go and talk to them these days, they'll say, "Yeah, well, this was a pretty idea. We were very excited, but it really didn't work, and we've given up on it."
Interesting. Yeah, and I believe Georgi or Glashow is working on the unparticle now, correct?
I know that Georgi. Georgi is the one with the unparticles. But anyway, they've done a lot of different things, but they I forget exactly when, on a time scale of 10 or 15 years after this, when the experimental results came in, they said, okay, well, we were wrong. This is just a bad idea. It doesn't work. That's one part of this. But maybe the thing to say to me, the more disturbing situation is you can go and, open a lot of kind of basic textbooks that we teach graduate students with, and they'll tell them the story. They'll tell them, there's this great, wonderful idea about unification, and here it is, and they don't really mention very clearly that it doesn't work. Okay, then supersymmetry was another kind of part of our kind of standard paradigm that we've been living with, and it also, the earliest standard model was written down in April. By December, people were writing down these supersymmetric extensions of the standard model. So let me explain what those are. This can get quite technical, but one way of saying the basic idea is if you understand there's this crucial relation between spinors and vectors. That spinors in some sense are a square root of vectors. They're mathematical objects that if you take the tensor product of two of them, you get a vector. And if you think of vectors as being corresponding to translations, we know that the world locally looks like a certain vector space of 4 dimensions, and you can translate in any 4 directions, and you get corresponding momentum or energy operators. And then there's also rotations, but what supersymmetry says is, well, you should extend your standard story about momentum and angular momentum and how it fits together into this Poincare-Lie algebra, and you get these generators. You should add some new generators which correspond to the spinor direction, which correspond to the spinors, and they're going to be anti-commuting, unlike the usual, the ones you know about, and they're anti-commutator. The fact that the tensor product of 2 spinors is a vector will correspond to the fact that the anti-commutator of 2 of these operators will be a translation operator. So that's the basic. It's the basic idea of supersymmetry. It is a beautiful idea, and so what you do then is you what people did starting in 1974 was you take the standard model, and you just kind of add some fields to it and things which then allow you to define this extended symmetry and define these new spinor generators, these Qs, these supersymmetry generators. And you could do that with the standard model. You could also play the same game with one of these grand unified theories. You could take your favorite grand unified theory and turn it into a supersymmetric grand unified theory. Okay, and again, so there's a lot of enthusiasm about this. I mean, a lot of it was also kind of driven by just the beauty of the idea. This is a really beautiful idea. If you try and do this, you find that these Qs commute with all of the this U1 SU2, SU3 commutes with these Qs. So you find what a Q is going to do is it's going to take any particle that you know about with certain charges, and it's going to turn it into a superpartner. It's going to produce a different kind of particle which has exactly all of the same standard model charges, but it has spin differing by a half because it has a spinor nature. So it has this prediction that, okay, well, and maybe I shouldn't say that completely. This wasn't completely enthusiasm. What you would have really liked to have happened was to look at the list of particles that you know about the standard model and find two of them that are related by one of these supersymmetry generators. If you had two particles that differed by spin, by spin half, and that had the same standard model charges, that would be a good candidate.
You would identify them as superpartners.
Yeah, those you'd have two superpartners, and anyway, and in some sense, that I think the problem is you don't see this. So you've had this beautiful new symmetry, but the problem is it doesn't relate any two known things. It relates everything you know to something you've never seen before.
I see.
So technically, it's this symmetry acts trivially on everything you know about. And so, okay, but you can then say, okay, well, this gives us a prediction of, we've only seen half the particles in the world, that every particle we know about is going to have a superpartner. That's kind of what you say. And some people, I guess, would take this enthusiastically. Oh, great, there's all these new particles in the world. I think I and many people were also a little bit, wait a minute, this is a little bit implausible that this doesn't, anyway, that there's this new symmetry, but we haven't kind of seen any of its effects. But anyway, so then the supersymmetry, there's a long story, but it goes into, the LHC is now given, has very, very strong limits on this. There really are no superpartners, and there's just zero evidence for any of this. Okay, so then you can do another part of the unification paradigm is supergravity and Kaluza-Klein, and again, these are things that were developed, a little bit later, but within a few years after the standard model. And supergravity is basically, you turn supersymmetry into a gauge theory, and it gives you an extension of general relativity. The gravitino is a partner to the graviton, and you have a theory which you could hope when you quantize it seems to have fewer renormalizability problems. That's a whole long story, but anyway, we had the supergravity theories, and then you also, going way back to early days of general relativity, people had been looking at what happens if you have more than 4 space-time dimensions. And so can you explain, one thing you might try to do is explain where does U1, SU2, SU3 come from by postulating more than 4 space-time dimensions, and it's these other so-called, kind of internal dimensions which explain everything. And that had been an idea that was wrong for a long time, but it became kind of a big part of this paradigm that people were looking at.
I have a quick question. So supersymmetry can be formulated at the classical level, correct?
Yeah.
Okay, so if you're putting supersymmetry on GR, then do you have a gravitino? Like, you don't have a graviton at the classical level?
Well, you don't have, so this would be, you'd have a gravitino in the quantum version. But you've got...
Like, does the classical version of supersymmetric general relativity have any properties that are wanted or that are studied? Or do people only care about it because it allows something interesting when you quantize it?
Well, the problem is that it's a problem with all supersymmetric theories. When there is a classical version of them, but the problem is that you've extended your standard kind of variables with these to get fermions, you've extended your standard variables with these anti-commuting variables. So it's kind of a weird. So classically, it's kind of a weird subject. It's So
you have non-commuting classical variables.
Yeah, you have it's non-commuting classical variables. So you can write down such a theory. You can look at it, but it doesn't kind of correspond to any. I mean, all of our intuitions about what's going on in classical physics, it doesn't really correspond to any of. You've got all these new degrees of freedom, which just have which are kind of different weird algebraic things, which aren't what you're used to thinking about.
I see.
So
now, someone like Elaine Conus, would he be comfortable with classical non-commutativity, or does he only study quantum non-commutativity?
Well, he's more interested. I mean, it's non-commutativity, but of a very specific sort. It's just it's what is sometimes called Z2 graded commutativity or super commutativity. It's like things don't commute, but the extent to which they don't commute is just something very, very minor, that they pick up certain things pick up minus signs when you interchange them.
Mm-hmm.
So I think someone like Alan Kahn or when people are talking about non-commutative geometry, they're often generally mean something much more seriously non-commutative, where it's not just Anyway, this is often, so mathematicians would often call this supercommutative, and actually the people who do kind of standard commutative geometry, they're used to having these little algebraic gadgets in it which square to zero and which anti-commute. That's also part of their story. It's kind of so. Some mathematicians would claim, it's really just part of commutative geometry. It's not like the non-commutative geometry that Alan Kahn wants. So now this is actually getting into the period when I actually remember, as I was a undergraduate starting in 75, and I was taking quantum field theory courses starting in 76, 77, and starting to try to pay attention to what was going on. And so I remember a lot of that this was kind of what people were talking about as the answer to these unification problems at that time when I first got into this. And like one example was Hawking gave his kind of initial lecture for his professorship and called, Is the End in Sight for Theoretical Physics? And he basically was saying, well, we've got this supergravity in this Kaluza-Klein version, and it looks like, that looks like it should give us a quantum theory which everything fits into and which is just going to explain everything. But anyway, there's the basic problem that none of this kind of worked out in the sense that, we've never seen any extra dimensions. We've never seen anything besides 4 dimensions. So there's really never been anything giving an indication that the Kaluza-Klein idea goes somewhere. Well, there's no gravitinos, and maybe that's a little bit unfair because it's hard enough to see gravitons. You're probably not going to see gravitinos either. But there's really kind of nothing. These ideas kind of never led to anything which you could go out and check it anyway, or if you went out and tried to check it, it wasn't there. So then that was kind of the situation in the early 80s, and then and people had been also studying these these string theories, and that's a long history we could don't want to really talk about here. But maybe one interesting thing is that the first superstring theory that the idea that it could describe gravity, that you could describe gravity using a superstring, was first paper about that was like a month after the standard model was in place. Anyway, but that kind of exploded in 1984 when Wick got into the subject, and there was a very serious interest in doing unification this way. And the basic idea there, anyway, there are a lot of things to say about it, but one idea is instead of thinking about particles at a point and fields based on those point particles, you think about your basic objects of your theory are one-dimensional extended objects. And then the idea of the superstring theories then was to bring together all of these things. So they had an E8 gut, they had supergravity as a low energy limit, they had extra dimensions of Kaluza-Klein going on, and so that they had everything. So I mean, this was kind of, I think one reason this appealed to everybody is there were all these ideas which hadn't really worked out, but now we spent all this time studying them. Now we can put them all together into this big new idea, which is going to explain everything. Anyway, and so people thought, okay, we got a theory of everything. I mean, Witten, who is an amazing genius and done amazing things, was very excited and telling everybody that this is the way the future is going to go. So that was 1984, and again, I mean, now 40 years later, there's kind of no evidence for any of the components of this, or including for the strings, and it just really hasn't. To stick to just kind of experimental statements, that there's absolutely kind of nothing anyone has seen of any kind which indicates any connection to this stuff. Okay, so now maybe I just want to kind of reason for going through all this is partly, I think physicists working in this area just don't make clear, the extent to which this just has not worked out. But I think if you look at all of this stuff, you see the same kind of generic problems. And, they're taking something which is incredibly successful, works perfectly, and they're embedding it in a larger structure of some kind, whether it's a larger gauge group, whether it's anyway more and more dimensions, whatever. But the problem is that they're doing this for various reasons, because it's some larger thing which they can compute. Maybe there'll be some new symmetries and some new things you can do, but there's no evidence at all for any of the components of this new structure. And then the problem is that once you've got this larger structure, you say, okay, it's got all these great properties, it's got these great symmetries, it's got supersymmetry, it's got larger gauge group, it's got all this stuff. But the problem is you then have to then explain, wait, why don't we see any of that stuff? You have this theory with all this new stuff in it, but we don't see any yet. So then you have to make the stuff go away, and you have to break all these symmetries. You have to make all your dimensions so small you can't see them. You have to make all your superpartners so massive you can't see them. You just kind of have to, yeah. And so all this business about the elegant universe and all these elegant, wonderful new ideas, rapidly turns into something, really, truly ugly, because it was all very elegant until you realize it didn't actually look like the real world. And you then have to start, turning the cranks and adding in various layers of ugliness to explain why you haven't seen any of this stuff. And I think this is a very conventional way in which a theory fails. You have some great new idea and you think it's wonderful, but then when people go out and don't see the things that this new idea predicts, you then have to, one thing you can do is you can be like George on Glass Show and say, okay, we were wrong, I give up, I go home, I'll do something else. But it's also very tempting to say, okay, well, there's a little bit more complicated version of the idea. I can add this structure into this theory or do something in this theory that's going to make explain why you don't see that.
Right.
And then you end up, but as people do more experiments, you just keep on having to make the theory uglier and uglier purely just to avoid making a wrong prediction.
At what point does it become more ugly than the beast you were trying to replace?
Well, but I would argue pretty quickly. But and I think the truly amazing thing about our history so far is that we've gone through 50 years of people being willing to make things just spectacularly ugly and unpredictable, and and not behaving like George Glass Show and just not saying, okay, this just doesn't work. Let's just face the obvious. I mean, the obvious conclusion is that this was just a wrong idea. But and how hard it is to get people to even admit that this is a sensible interpretation of what's happened in the last 50 years is kind of why I'm going through all this. Okay, and anyway, and yeah, so this was just more of what I wanted to say on this. And I think what's actually happened is, lots of people keep trying to push through these old ideas that don't work. But, I think many people and kind of the most serious people in the subject, just kind of stopped working on these. They don't go out and say, okay, these things are failures, but they just kind of stop working on them. And if you ask them about it, they say, well, I just don't see how to push this any farther. I still think it's a beautiful idea. I mean, I don't want to put words into Witten's mouth, but I don't. I think if you would ask him about some of this, I think he would say, well, I still think it's a great idea. I still think it's the best possible idea we have about how to get answers for unification. But unless some experiment comes along and tells us some new hint as to how to make these things work, it looks kind of hopeless, and I'm not. And so I've kind of stopped thinking about it every day. And so I think the kind of new ideology is kind of turning into, well, let's not admit that this thing failed, but let's just kind of say that it's now thinking about unification is now no longer something a serious person should do, because it's just hopeless until somebody has a really brilliant new idea, until we see until the experimentalists help us out. We're just not going to be able to move forward with this. And this is something I see a lot talking to theorists and seeing what they say. They really, the idea of thinking about unification is becoming something that is kind of a crank activity, in the sense that this is something that only a crank would do now. Only you have to be some kind of amateur or crank or not really know what you're doing to realize that, look, the smartest people worked for 50 years on this, and that this was the best possible way of doing this that they found, and they haven't been able to push it and make it work. So, it's just, what are you going to do?
Well, you mean to say unification attempts outside of string theory, or to not even consider string theory a unification?
Well, I mean, the string theory then becomes a complicated question. Is what do you mean by string theory? But I guess one way to maybe a better way than specifically going on about string theory is to think of string theory, guts, supersymmetry. I really want extra dimensions. This really is kind of that has been the paradigm that we've had for 50 years, and so the question is, and I think the problem with anybody who's trying to say, okay, well, that what you guys have been doing for 50 years is just completely doesn't work. You have to do something completely different. I'm going to tell you about it. I mean, that's a hard sell, I think, because people say, well, wait a minute, we're 50 years, this is geniuses have been working on this, and these are all great ideas, and this is wonderful. How can you tell us, that this is all just wrong? You must, why? That's the kind of, that's like these crackpots who tell us that, Einstein must be wrong, So it's always been a hard sell to say, look, everything you've been doing for all this time, everything you should forget about it. I want to tell you about something quite different. That's always been a hard sell, but it's still a hard sell. I think it would become less of a hard sell if people would actually admit that, wait a minute, this was all just wrong. You really have to look at very different things. But I don't think that you're really seeing that kind of case made that, that we have to look at we have to go all the way back to 1973 and look at different things, not the things that we started looking at back then.
So on the one hand, you put something into the oven and it needs some cooking. There's the fear that if you take it out too soon and you prematurely dismiss it, perhaps SU5 was a great idea, you don't dismiss it after the first year, you investigate it some more. But then there is the opposite phenomenon of overcooking. And you have to admit when something has become burnt. Maybe it's been burnt after 50 years in the oven.
Yeah. Yeah. So that's always a question. At what point do you, do you give up an idea? Did you say? And in some sense, I mean, my argument with the string theory always was from the beginning that, my judgment of what's going on is that you guys, this is you really have to give up. This is something which hasn't worked out. Their argument was, well, we still think it's the best thing we know how to do. We still think it's worth pushing forward. So it was kind of it's kind of hard to argue about that. But, I think things have changed over the last 20 years. It's just it's just become clearer and clearer that this stuff just doesn't work, and this argument that we have, and it's gone from like, oh, we want to keep working on it. No, maybe within 5 or 10 years we'll have something new and we'll have made progress. And now you ask people talk about, well, it may take 500 years for us to make any progress on this. And
right.
This is taking longer than I thought. Okay. So anyway, but
take your time. Take your time. Firstly, just for people who have gotten this far into this talk, this is the quickest recapitulation of the standard model and the state of affairs of physics that probably exists online. It's been 40 minutes or so, and you've gone through the state of physics since 1915 to the 1970s, and then to the present day.
Well, but I haven't really explained a lot about it, but and the bottom line is, I think, more depressing that you shouldn't actually study any of it. The post 73 stuff you shouldn't just study it. You should try to find something else to do. So now there's a much shorter and much sketchier part, which is to kind of end about what I've been trying to do. So let me start about this. So maybe the thing to say about this is actually when I was a graduate student. Let me go back. I worked on doing these lattice calculations of using SU3 gauge theory, where and the calculations just used the gauge fields. You didn't use the matter particles, and so there's a really beautiful way of putting gauge theory, of discretizing and putting on a lattice, and so I really worked a lot on that, and I thought that was great. And so then I thought, well, wait a minute, what about the matter particles? What happens when I put them on the lattice? And I started to realize that, wait a minute, matter particles are these spin 1/2. The spin geometry is really weird. It's not at all obvious, how to capture that geometry and while how to preserve any of that geometry when you discretize things. And there's a long story about people trying to put spinor fields on the lattice, and you end up with all sorts of interesting problems. And that's when I first started thinking about some of these things now. And I had some kind of vague, very, very vague version of the idea I'll be talking about, one little piece of it, and thought about that for quite a while. And then, but at some point I gave up on it. I decided that this wasn't giving up because there's no experimental evidence, but I just gave up on it thinking, okay, everything that I know about this subject says that, this just is not going to work. This is implausible. You can't make that happen. It's just,
Everything you know about the subject forbids you putting fermions on the lattice?
no, we'll see. I'm going to make a certain claim about that symmetries do something very odd you didn't expect. And I'm just saying that I had that very vague idea that maybe that should be possible, but at some point I convinced myself that, the way space-time symmetries work is clear enough that you just kind of can't have I now believe happens. I had convinced myself could not possibly happen. And so,
interesting.
Anyway, just had some history of my own personal history. And it's within the last 3 or 4 years that I finally, thinking about this some more, and also a lot that I've learned actually by teaching courses on quantum mechanics and QFT and kind of writing a book about that and starting to understand, very precisely exactly how these symmetries work. I started to realize I'd always assumed that, there was some simple explanation for something that you would see once you wrote down the details of how these symmetries worked. And then what I just found as I started writing down the details and learning more about it is that just wasn't there. It really wasn't there. And then I finally started thinking about it in different ways. I started to see that, wait a minute, this actually there's a perfectly coherent way of thinking about what I thought couldn't possibly happen. There's now perfectly good reasons to believe that it could happen.
Sorry, and that occurred to you while you were writing the book on quantum theory and representations?
Yeah, more later after that was done, and yeah, but yeah.
So which book are you referring to that you were writing, and it elucidated ideas to you?
Well, no, it was kind of after writing that book, but I've also taught that course several times, so when I say writing, I keep thinking, okay, I should improve that book and do some more things, but it's never really got written down. But
I see.
I should say that. And I've also, anyway, so maybe that's a better way of saying it. So, but that was writing that book first got me, and actually it was one motivation in the back of my own motivation for writing that book was to kind of get the story of these space-time symmetries written down very clearly. And so that I could, some things which I never understood exactly how they happened exactly, to get it all written down. And as I started to get it all written down, I realized, wait a minute, I'm not kind of seeing the, the thing which I was convinced would have to be there that would explain why that would make clear why this couldn't work.
All right, so let's get to the approach that seems promising, as this is the hugest tease that we just...
Yeah, sorry.
That I just kept asking you questions. That's my fault.
Oh, that's
left
fine.
The audience hanging.
And I'm sorry, you're not going to get a detailed answer to this anyway, but you'll see. But first of all, maybe just to say to put this in the context of what I was talking about already, is to say that this is how about 4 dimensions. So no extra dimensions, 4 dimensions, and the idea is that the reason we don't see any extra dimensions is that there aren't any. It's all about 4 dimensions. And you should look very carefully at 4 dimensions and ask, what is very, very special about 4-dimensional geometry? There's a lot of very interesting things that happen only in 4 dimensions.
Uh-huh.
And, and can we use those? And especially the geometry of spinors and twistors. I won't really get into twistors, but twistors are a very beautiful idea to understand conformal geometry in 4 dimensions, and they're very, very tied to 4-dimensional geometry. They really are. So it's an idea of Roger Penrose's, but there's part of the whole story of the spinors.
Yes.
But the other thing which I'm trying to use, which hasn't really been used very much, I think one thing to say about all of this, all the story that I told you, if you go and look at any of those books about any of these guts or supersymmetry or supergravity or string theory, you'll find one strange thing if you start to dig into the technicalities, that our space-time has this so-called Minkowski metric that you put a minus sign on the distance squared in time,
Mm-hmm.
and if you try and write down his theories in any legitimate way, you find that there are technical problems if you try to do it in this indefinite Minkowski signature. So what you do is you assume that you look at his case as if all 4 dimensions were the same, as if there was no distinguished time, and then you write the theory there, and you do something called Wick rotation to recover what happens in Minkowski spacetime. I think, if you look at all the literature on all the theories I've been talking about, there's really, in every case, it always is like kind of a technical problem. But wait a minute, don't we need to do this in Euclidean signature? Are we doing it? How is it going to go from one to the other? And it's kind of a technical problem, which was there for all of these theories, but people just kind of tried to avoid thinking about it. There was always a feeling, okay, this is some technicality, maybe some mathematician will figure it out. We don't care. We're just going to write down formulas and hope for the best. But this is something that it really struck me that you really, this relationship between Euclidean and Minkowski signature was a really interesting topic.
It was indicative of something?
Well, it was something we really didn't understand. I mean, it always, in my mind, I mean, we have this standard theory. There are parts of it that I look at it and say, I understand that perfectly. It's beautiful. It all comes from a simple symmetry argument. There's no technicalities are easy. That's done, cooked. That's it. There are other parts of the subject where you look at something and say, wait a minute, there isn't a clear explanation for exactly what's going on here. And that's this Wick rotation was a place that happens in the standard model. So anyway, so the main new idea is to say what I'm trying to do is to claim that this Wick rotation, if you think about your geometry in terms of spinors, it changes the geometry, the spinors in a very fundamental way. That the geometry of spinors in Euclidean signature and the geometry of spinors in Minkowski's signature is actually quite different. And the basic idea, this is the idea that I had going way back, which I didn't think could work, but which I'm now convinced does, is that in the four-dimensional rotation group, I'll say more about it, but it breaks up into two SU2 factors. And the idea is that when you Wick rotate to Minkowski spacetime, one of those two factors is going to be a spacetime symmetry. The other one is going to be an internal symmetry.
Okay. Right. Interesting.
And this provides kind of a new unification of internal and space-time symmetry. So these things get unified on the Euclidean side. And it just involves the degrees of freedom that we know about. There's nothing extra. But it's the new thing is to say, wait a minute, it is to say, look, you really should think about what's going on at the Euclidean signature, and you should realize that there's a very important subtlety when you try to make spinors go back and forth between these Minkowski and Euclidean.
So let me see if I can do a quick summary. There's the Pythagorean theorem. It's a squared plus b squared equals c squared. And that's for 2 dimensions. And then if you want to do something in 3 dimensions, it's like a squared plus b squared plus c squared equals the hypotenuse or whatever you're trying to measure. You have to take a square root. But the point is that you have something plus something else plus something else. Now, in Einstein's theory, you have something plus something minus something else. And that minus causes some issues. For instance, with the Feynman path integral, it creates an oscillation. So sometimes you want to do something called Wick rotating, which means that you take that minus sign, which is technically an imaginary for technical reasons, into something that's a positive, into something that's a real number. So that you have something plus something plus something plus something. And that's a much nicer space to be in. Additionally, you have this low dimensional coincidence with spin 4 being akin to SU2 cross SU2 more than akin. They're equivalent or isomorphic to it. So I thought you're going to use SU4.
Okay. Actually, maybe let me go on that. So it's more SO4, but I was going to say a bit more. Let me specifically answer some of that because I'll try to explain. So this was just kind of an overall, and let me see how much I can do of that. Okay, so let me just first, so this is, Wick rotation. So another way of getting this minus sign on the square is to change from, put in a factor of the square root of -1.
Mm-hmm.
So what this is, Wick rotation is, what it's supposed to be doing is you've got a theory, a time variable, and it's saying, okay, you can make the time variable complex, and then look at a theory where your time has become purely imaginary, okay? And then that minus sign there, which is going to, when you multiply this by itself, the two factors of I are going to cancel that minus sign, and everything is going to be plus. So the idea is that there's also so sometimes I refer to this as going from Minkowski, which is real time, to Euclidean, which is imaginary time. So I'll go back and forth between saying Minkowski and Euclidean, or real time and imaginary time. But you can do this even for the simplest quantum mechanical models. You can start thinking about what happens if I make time imaginary, and that's simplistic version of Wick rotation. Here's the problem when you try and do this in quantum field theory. So if you how are you going to do this? This starts to get a bit technical, but if you a quantum field theory, you've got these field operators, and they depend on time. Now, if you say I'm going to make them depend on a complex time, so then what happens is that these fields in this Heisenberg picture, if you change time on them, you're conjugating by the Hamiltonian operator.
Right.
That's the Heisenberg picture. So what this is saying is that if you try to go to imaginary time, if you make imaginary time non-zero, you're going to conjugate by this operator the exponential of the imaginary time times the Hamiltonian. But now here's your problem. The Hamiltonian, its eigenvalues are the energy, so it's an operator that has a spectrum which is all at positive energy, but which goes off to infinity in the cases we're interested in. So, a typical theory of even of a simple particle, it has to have positive energy, but it can have arbitrarily high positive energy.
Mm-hmm.
So now your problem is that, you've got these two operators, e to the tau times h and e to the minus tau times h. And if tau is positive, this one is going to make sense, because it's e to the minus something positive times something positive, whereas this one's going to be a problem. This one is just going to become exponentially large. Whereas if tau is negative, then it's going to be the opposite. So there's just a fundamental issue, which everything we know about quantum field theories and the operator formalism, you can't analytically continue the theory. You can't make time complex and have it behave the way you want, because you're going to immediately have the rules for what's going to happen to the field just don't make any sense. You can't do it. So that's what happens in the operator formalism. But the other formalism you have for writing down quantum field theories has the opposite behavior. If you write them down as path integrals, if you go to imaginary time, this Euclidean space-time, then the path integrals are e to the minus something positive and large, and they make perfect sense.
Mm-hmm.
So you're integrating some kind of Gaussian thing or something that falls off at infinity very nicely. But if you try and do this in Minkowski space-time or real time, then what you find is that you're trying to integrate over some infinite dimensional space e to the I times something. So you're integrating this wildly varying phase over an infinite dimensional space, and this you can't. It actually just doesn't make sense in any sense as a measure or as a real integral. Okay, so these two kind of formalisms we like to use to do quantum field theory, they have opposite. People will talk about them as if you can use them to go between imaginary and real time, but you can't. I mean, one of them works well in real time and is kind of a formal object in imaginary time. The other one is the opposite.
I'm confused. Are you saying that Wick rotation is defined in the Feynman case, but not the operator formalism? Because if those formalisms are physically equivalent and you can translate between them, why would it work in one but not the other?
Well, I mean, I'm saying you can't Wick rotate either one. I'm just saying.
I see.
I'm saying these two main formalisms for how we know how to write down a quantum field theory have, one works in one case and doesn't really work in the other case, and the other was the opposite. So if you tell me I want to understand how to go back and forth, we don't have a theory that does that.
I see.
Okay. Yeah. So we don't. There is no such. This took me a long while to realize that there is no such thing as any kind of full theory in formalism, which depends upon complex time analytically and allows you to analytically continue between time and imaginary time. There just is no such thing.
Now, is that problem in both directions? That is, if you start with the Euclidean and then you try to get Minkowski versus the opposite?
Yeah, because only one of these works. Depending where you start, you've only got one that really works, and But if you try to start with either one and get to the other, you can't.
Yes. I get it. Yeah.
It just doesn't work. So, and okay, but there is something you can do. So what you can analytically continue the theory. So you can't take your operators, states, measures, and all these things and analytically continue them. But what you can do, there are things that do analytically continue. So you can define these things called Wightman functions. They're just vacuum expectation values of operators. So you take a product of two operators at two different spacetime points, you multiply and you apply them, you hit the vacuum with them, you get another state, and then you take the inner product of that state with the vacuum again. And anyway, and you get things depend upon X and Y. And these kind of carry most of the information about the theory in them. And so if you have an operator theory, you can compute these objects and you can characterize the theory, a lot of the theory by these objects. And they're kind of, the operators don't commute, so this thing is not symmetric in X and Y. If you interchange X and Y, you're going to get something different. They're also, technically, these are distributions, they're not functions. These are things more like delta functions. They don't make sense as actual functions, but you can kind of take convolution of them with functions and get something that makes sense. That's what you can do in real time and operator formalism. And then in the imaginary time and the path integral formalism, you can take similar things, which are moments of these. Anyway, similar path integrals are kind of moments of these measures, and they correspond in a one-to-one way with the Wightman things, except that they're symmetric. But it's a very different kind of theory. It's the calculation you're doing and the whole theoretical setup. There's no states, there's no operators, there's just these measures and these integrals, and they look a lot more like what you do in statistical mechanics. And actually, they're really kind of, one of the amazing things about this whole story is that if you take your imaginary time to have a finite extent of size beta, and you do this calculation, it's precisely a statistical mechanical calculation at a temperature, given by beta is equal to 1 over k times the time. So it's a very different. The path integral formalism really is much more like a statistical mechanical system. It's very different than the operator formalism. But the output of it are some functions, the Schwinger functions, which can be analytically continued to the Wightman functions.
Okay, now let's get to SO4. I'm interested how you break it to Lorentz.
Okay, so but the philosophy I'm pursuing, what you're supposed to do, what I believe is that the theory really makes you should think about the theory in Euclidean space-time or in imaginary time, and then you can compute the Schwinger functions. But now if you want to have states and operators and the whole operator formalism, you have to do something which is often called you have to kind of reconstruct the real-time theory from the imaginary time theory. You can't just analytically continue. And sorry, this is where I'm rapidly kind of getting into talking about complicated things which I can't tell you anything about. But you can do this, and one thing you have to do is in 4 dimensions, you do have to pick one direction, say that's the imaginary time, and you have to have an operator which just kind of reflects you in that direction, and that's called the Osterwalder-Schroeder reflection. And you can use that to reconstruct the real-time theory from the imaginary time theory. I'm not telling you how to do it, but you can. But the maybe just something to notice is that, so if you construct operators and states in real time, there's no distinguished direction of time in real time, and you've got positive and negative time like cones, but the construction of operators and states and everything you do in real time doesn't have a distinguished direction. So this is what it took me a long time to realize that this was and this is when I started to realize that what I had been thinking about years ago could work, is that Euclidean spacetime is quite different, because in Euclidean spacetime and in the imaginary time, you have to break the SO4 four-dimensional symmetry and pick a distinguished direction.
Yes.
You have to do that.
Yeah, it sounds like your theory is introducing another problem of time. There are many problems of time. There's one about how is GR different than QM, and how is
it's a different direct way.
There's the Woitian problem of time.
These are imaginary times, so that's a different thing. But this is what it took me a long time to realize, and what was kind of maybe will first kind of break through when I realized that this was going to work, is that Euclidean theory has no operators or states. If you want to have operators and states and you want to get back your physics, you have to break the SO4 symmetry and pick an imaginary time direction. Okay? And this turns out that this is known. But the problem is really what happens for spinors. So it's kind of known, and you can read about this a lot of ways for scalar field theories, for theories that don't involve spinors. But what happens when you try and do this for spinors has always been mysterious, and there isn't really any kind of convincing. Well, anyway, there's some early papers on it, but there's really a lot of people have tried to figure this out, but anyway, not what to say. But my basic proposal now is that something really unexpected happens right here. That what was a space-time symmetry in the Euclidean QFT becomes an internal symmetry in Minkowski QFT exactly because of what you have to do when you try and do this reconstruction procedure and you introduce this Osterwalder-Schroeder reflection operator when you do it with spinors. That's the basic one basic thing I'm saying now. Okay, but and now here's just a couple of minutes on spinors before I do that. But maybe the one reason this is, I kind of said this before, that spinors are really different in Minkowski and Euclidean spacetime. But the basic idea is that in Euclidean spacetime, the rotation group SO4 has this double cover, which is 2 copies of SU2, which we'll call left and right. And the matter particles are these Weyl spinors that are either, they're these C2 represent just the SU2 acting on C2, either the left-handed one or the right-handed one. And the standard story about Euclidean spacetime is that if you want vectors, you take the tensor product of the left-handed ones and the right-handed ones. Anyway, so this is the story. And in Minkowski spacetime, you've got spin 3-1, you have this different treatment of one direction, but that's a very different group. It's not SU2 cross SU2, it's SL2C. It's 2x2 complex invertible matrices with determinant 1. So there's only one kind of a spinor in some sense. Then there's only one two-dimensional group. It's acting also on a C2. So you have one kind of spinor I'll call S. But now you can also look at the complex conjugate. And the complex conjugate B. Anyway, so the complex conjugate is a somewhat different thing. It's not true for SU2. And in Minkowski spacetime, vectors are tensor products of 2 kinds of spinors, but they're the Weyl spinors times their conjugates. So the point is just that these are just 2 kind of completely different things. And now just to this is where I'm starting to run out of steam here, but maybe just kind of a last kind of important thing to explain, which it also took me a while to realize, is about the Dirac operator. That maybe it's important to realize that the Dirac operator really is a vector. When you write down the Dirac operator, people write it down, using these kind of upper and lowered indices of, normally you make Lorentz invariant things by putting together a vector and a dual vector, and you contract and you get something which is a scalar. So when people write down the formula for the Dirac operator, they use that formalism and they make it look like what they're doing, but that's just not true. I mean, the Dirac operator is not a scale. It's not a Lorentz scalar. The Dirac operator is not Lorentz invariant. The Dirac operator transforms like a vector. It transforms like a vector under Lorentz transformations. And if
Wait, can you go back? Can you explain what is the common account? What do people ordinarily say about the Dirac operator, and what is it that is the truth about it?
Well, I mean, people don't say something directly wrong, but I would just say pick any kind of physics book that explains relativistic quantum mechanics of the Dirac operator and look at the discussion of how does the Dirac operator behave under Lorentz transformations. I mean, they're writing down formulas, so you'll see that there's a non-trivial transformation formula. They'll write it down, but if you try and people will have very confusing things about what the meaning of that transformation formula is. I'm just saying the meaning of that transformation is very simple. That the Dirac operator is not what the notation makes it look like, which makes it look like a scalar. It's a vector. And if you understand the relation between vectors and spinors,
I see. Okay.
It's just a vector. And it's maybe a little bit easier anyway, so Dirac operator is just a vector. And that's rarely, if anywhere, said, though the formulas people are writing down, they say that, but it's not the way people think. This is now I'm finally getting to the end of this, where this will become completely incomprehensible. But so if you try and think about what is Wick rotation, you try and think about it as analytic continuation from Minkowski to Euclidean spacetime. What the standard way of doing that is thinking about complex space-time, making not just time complex, but all of space and time complex.
Okay.
And then so it's a complex four-vector. And then you look at the rotation group or spin group in four complex dimensions. You realize it breaks up into these two SL2Cs. And these complex four vectors, again, it's just like in the Euclidean case, they're just a product of a spin representation of one SL2C and spin representation of the other SL2C. Now, the standard story is that this is all supposed to be a holomorphic or analytic story. Everything is supposed to depend, and everything is supposed to be analytic, and all your complex variables are holomorphic. And so Wick rotation is then this analytic continuation in this complex spacetime. So now the new story I'm trying to tell is basically that one way of saying it technically is that if I'm going to do Wick rotation, I'm not going to do Wick rotation by this analytic continuation. That actually doesn't work or doesn't do what I want to do. But I am going to do Wick rotation starting with the Euclidean story and doing this reconstruction of the real time theory. And I need an appropriate Osterwalder-Schroeder reflection for spinor fields. And this is what I'm kind of in the middle of trying to get this written down carefully. But what I can see happening is that when you do this, the new thing you have in your Euclidean spacetime is you have a distinguished imaginary time direction. And that means you're going to have a distinguished Clifford algebra element, gamma zero, which is going to be, you get distinguished elements or gamma matrices, if you like, in the physicist language corresponding to the different directions. Well, there is a distinguished gamma matrix corresponding to the imaginary time direction. And that interchanges left and right. If you hit a left-handed spinor with it gives you a right-handed spinor and back. Exactly, because it's a space-time vector, exactly. So it takes one to the other. And so what gets Wick rotated to Minkowski space-time is not this tensor product of left and right-handed spinors in Euclidean space, which is the vector space, but something where you've hit one of them with a gamma zero. So you're actually looking at so vectors in Minkowski spacetime should be thought of as tensor products of two right-handed spinors.
Uh-huh.
And so the geometry in Minkowski spacetime is not what you thought it was. It's not the analytic continuation you thought it was. It's something different.
That looks spinorial, like making an analogy back to the beginning where you said that spinors can be thought of as the square root of vectors.
Yeah. Well, all of these statements about vectors being different tensor products of different kinds of spinors, those are all the kind of thing that goes into discussions of the supersymmetry. I'm doing something a bit different. They people then, and some of the things that I'm talking about, they always appeared. It's very interesting. If you go look at the literature of supersymmetry and you ask, wait a minute, what happens to supersymmetry under Wick rotation? You'll find that. Anyway, you'll find a very, very confusing literature, let's just say.
Yes.
But anyway, so this is just to explain that the body. So this is actually, we're at the end. I just wanted to explain the slogan, and the last paper I wrote was a short paper trying to emphasize this, but from a different point of view. And the slogan is that space-time is right-handed. That when you're in Euclidean space-time, you've got vectors.
Interesting.
Vectors are tensor products of left and right, but when you do Wick rotation, you just have right times right, and so these left-handed spinors really are an internal symmetry. You can still think about them once you've Wick rotated, but they're not space-time symmetries anymore. Anyway, and so the slogan is, that as far as space-time symmetries are concerned, you've just got you're just dealing with right-handed spinors. These left-handed spinors that you had before Wick rotated, they have nothing to do with space-time. They have to do with the internal SU2 symmetry of the Wick interactions.
Was there an element of chance, like in your theory or in your mind? Was there? Firstly, wonderful talk.
Okay,
wonderful talk. We'll put in some applause.
Okay,
here.
Thank you.
Wonderful. Okay, was there some degree of chance to what made space-time right-handed versus left-handed?
Oh no, that's just a matter of convention. So I mean, what I call left and right is a matter of convention, and I mean the one thing one interesting thing to say about this, and one reason for thinking about twistors. So I haven't actually gotten into the relation of twistors. Is that if you just think about the standard formalism that's in the QFT books, where you have gamma matrices, whatever, that standard formalism. That formalism is kind of left-right symmetric, and it's actually set up to work very nicely when you've got parity invariant theories, which you can interchange left and right. So you have to kind of add some things into that formalism to kind of project out whenever you have symmetry. Anyway, so but the thing which is different, and I haven't talked about twistors at all. Twistors are a different part of the story, but the twistor geometry is very, very much asymmetric. So twistors, when you write down twistors, you say that points in space-time basically are spinors, but they're spinors of one kind. They're just the right-handed spinors. So twistor geometry also has this kind of, in an interesting way, the same kind of aspect that it's left-right asymmetric, and you have to take one of them as a fundamental thing. It's telling you what the points are, but I'm doing something different than the usual twistor story because I'm treating vectors differently than what's going on in vectors.
My next two questions may be related. So, where is gravity in this? Sure, we have space-time, but we've been dealing with flat space-time, so that's one question. And then the second one is, what happened to Euclidean twistor unification? Is that related to this?
Yeah, okay. So this is just a part of. Well, maybe let me try to answer them in order first. So first, the we know how to write down general relativity as a as kind of a gauge theory formalism, and that SU2 right. So you can write down gravity, and this is something which, if you look at the people who do loop quantum gravity, and they talk about things called Ashtakar variables. Well, they so gravity written in terms of Ashtakar variables is written down in this very asymmetric way, and it starts to become a long story, but one way of saying it is that I had these two SU2s, SU2 left and SU2 right. SU2 left is an internal symmetry. That's the theory of the Wick interactions.
Yes.
SU2 right is a space-time symmetry, and gauging that is part of this is basically how you get general relativity. You gauge that, but then you also have to tell me what you're going to do with the vectors. But if you tell me what you're going to do with vectors, and you gauge that SU2 right symmetry, you can get general relativity that way. It's general relativity kind of in Ashtakar variables.
I see. Well, for people who want to delve more into the details, we'll leave the links to your papers on screen. We'll show them currently. They're on screen. And then also, you and I, Peter, we have a podcast on theories of everything. I think it was 2 hours or 3 hours long. We went quite in depth into these theories, although space-time is right-handed came up a few weeks or a couple months afterward, but the Euclidean twister unification, I believe. So people can watch that if they're interested.
Maybe something I should make clear is that, so I've written various things about this, and the Euclidean twistor unification is kind of part of, maybe a good way to say it is that there are a lot of things about this Euclidean twistor unification proposal thing, places where I really did, I specifically, like I said, look, I don't understand what's going on here. What I'm saying here is much more of an answer to parts of that story. There are parts of that story which were, I thought, I can see here's some things are going on that look like you can really do something with them, but there's a lot that I don't understand, and this is more of an explanation of things that I didn't understand there. So you have to then go back and see how I can use that there. The other thing to say is that this is really just kind of an ongoing program. I mean, I keep trying to write up a better version of the stuff I've done in the past for this, and when I write it up, I start to understand something much better and see it from a different point of view, and so I stop writing and start doing something. So it's
I see.
It's an ongoing process, and so sooner or later there are no technical details here, and so like what's on this slide here, I can't. You're not going to find anything that I've written down that explains the details of that. It's still something that I'm working out the details for myself and have to. I mean, it's clear something like this is going on, but the exact details are still not in place. This is a point of view I've been thinking about a lot in the last month or two, and it really it seems to come together really nicely, but it's very, very much not written up. And if I try and write it up, I may find that this isn't quite the right thing to do either, and it'll be something different, but we'll see.
Thank you, Professor.
Okay.
We'll also link your blog on screen, and that's something that I recommend.
Yeah, and one thing since I'm having trouble getting some of the stuff written up, one thing I keep thinking about is to try to use the blog to kind of, as I understand pieces of this story, to write up something about those pieces there, it avoids being kind of a formal, completely coherent paper, but at least if I say, okay, now I understand.
Many people are reluctant to do that because they feel like their ideas may get swiped.
Well, I mean, yeah, that was. I guess I've started to realize, I should say maybe when a lot of this stuff first occurred to me, I thought, okay, this is really cool. This is a great idea. The more I think about it, the more this works. I'll just start telling people about this, and people complain, there's no good ideas. They don't know what to do. Lots and lots of people are going to get interested in this. And what I found is that nobody really seems to understand what I'm talking about or be getting very interested. So the last thing I'm worried about at this point is people coming in and swiping my ideas. I'd be very glad.
Yeah, you'd be glad. Yeah,
wonderful. I would hope if anybody who wants to kind of try to swipe any of the ideas and who's interested in doing something with them, please go ahead.
Right. At least they care. Okay.
Yeah. So I actually want to get some of these things, figure out how to get some of these things out there and get people to understand some of the things I'm seeing, and I hope that some of them will then appreciate some of what I'm seeing here and start kind of help pushing it forward.
Well, thank you for appearing on this series on rethinking the foundations of physics.
Hey, sorry about that. I thought it would be half an hour, but I guess not.
That's perfect. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. There's now a website, Jaimungal.org, and that has a mailing list. The reason being that large platforms like YouTube, like Patreon, they can disable you for whatever reason, whenever they like. That's just part of the terms of service. Now, a direct mailing list ensures that I have an untrammeled communication with you. Plus, soon I'll be releasing a one-page PDF of my top 10 toes. It's not as Quentin Tarantino as it sounds like. Secondly, if you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen? on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.